Welcome to the course of material selection for mechanical design, and we have crossed module 1. Now we are in module 2. Module 2 will focus on mechanical properties of materials that are relevant for design. So, initially what we have seen? We have seen it from the material attributes point of view, and now we will be talking about mechanical properties of materials, and this will be done in a series. So, today will be the first of this series. So, this will be the lecture 5 towards this direction. Now, what exactly we have covered in module 1? Let us quickly recap, and then we should be able to integrate it with our new knowledges of module 2. In module 1, what we have talked about is that I have given you first of all an introduction to the material selection for mechanical design, and I wanted to also tell you that this is not a course on simply properties of a material, but in a much bigger sense that how do we select a material for product design. That is what is our intention. So, whatever knowledges are required towards that direction, we are sort of accumulating all of them. And I started for that, keeping products in mind. I talked about the clocks, if you remember, that I said that suppose 3000 years before, if you have to design a clock, what were the material requirements, attributes of the material, and how the materials were chosen. And in comparison to that, if you want to design a clock today, then what are the material requirements that will be there. So, that is what was the very fast discussions in this direction. Then I have come up with a little more sort of uh, formal way of introducing the topic to you by actually uh, arranging the problem of material selection part for 2 points of view. One point is from the point of view of tension, compression and bending. So, that was the material selection for tension dominated design, followed by, of course, I have talked about that compression and bending. And then we have seen that at this point we have introduced something which is known as the Ashby index, and we have seen that for simple tension, compression and bending, what are the corresponding Ashby indices. Then in the last lecture, we have talked about the torsion and shear dominated design part, again corresponding material property indices. Also, I introduced to you the concept of Ashby triangle, where I said that it is not just material. When we select a material, then there is always the material part of it through the material property index that is there, but also the shape comes into picture. We call it the geometry G, and also the process, that what sort of manufacturing process we are going to adopt. So, this becomes a simultaneous process when we are selecting a material. We have to always continuously think of, okay, what is the shape we are going to finalize, and then how we are going to manufacture. Instead of thinking of these problems separately, you need to think of it simultaneously. That is the spirit of something which is called concurrent design. So, that is what we have adopted, and we will adopt all throughout this course for product design. Now, with that recap, let us come to the new part, that is today and this week we will look into all the mechanical properties that will be relevant for us, okay, for different types of product designs. Now, so that while talking about it, I have to talk about basically one of the important group of properties which are related to deformation and strength. So, from that point of view, I have to introduce the concept of stress and strain, and then I have to talk about extending that towards tensile strength, towards ductility, towards brittleness, resilience, toughness and impact strength. So, all these things will come one by one once we understand the basic concept of stress and strain. So, now if we look at it, that the classes of property affecting the product design, just a bird's eye view, let us say, we just take ourselves out suddenly and we try to see that, okay, what are the things that are coming up. Then of course, we can break it into broadly 8 domains. Okay. The first domain that will come up is the economic and environmental effect. Okay. That is very, very important. While choosing a particular material, that must be one of the very crucial factors in today's design, because everything we do has to be in the domain of sustainability. So, now in that direction, what are the properties we have to look into, like price and availability of the material. Okay. So, whether it fits our sort of a cost for that type of a system. See, there are certain products that are actually mass products. So, their cost becomes a very important factor. Okay. There are certain products which are safety products or defense products or space products. There the safety takes the predominance and hence cost is not so important. You are ready to spend more provided you get more safety. So, then the price is accordingly changes actually. Availability is of course related strongly with the price. And then as I told you that today we are more conscious on the impact on environment. So, the recyclability of a material is important. Certain materials we know that they are highly recyclable, like steel, like aluminum, they are highly recyclable. On the other hand, if you go for materials, for example, which are related to polymers or plastics, then recycling of such materials is a problem. Okay. Some part of polymeric groups are easily recyclable, like thermoplastics, and some are not. For example, thermoset polymers, they are not. So, they degrade a lot. So, sustainability is very important, sustainability and recyclability of a material. Then another important thing comes under this domain, that is the carbon emission. Okay, because anything we do, if that involves the emission of carbon monoxide or carbon dioxide, that is going to enhance the greenhouse effect and the environment will be heavily polluted. So, that carbon emission we try to reduce it. So, this is also sustainability point of view, recycling is one aspect and carbon emission reduction is another important aspect. Now, together all these things, that group we can actually keep it as economic and environmental effect group. Then the second group comes, which we will be focusing today, that is the elastic modulus, all sort of mechanical properties, okay, of a material. For example, elastic modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength, damping, just to name a few. Okay. These are by no means these are an inclusive of everything, but these are some of the important properties, just example of it. And then we come to the other part, which is the thermal part. So, thermal properties may be thermal conductivity, specific heat, thermal expansion coefficients, etc. Then the fourth group are the general physical properties. For example, density is a general physical property which always bothers us, because we will talk about how to make a structure lightweight. Okay? Lighter weight means lesser energy consumption and also it is more sustainable, and if something is lighter, then it is also portable. So, those things increases. Now, electrical and magnetic properties, that comes wherever the mechanical system interfaces with an electrical system. Okay? For example, you are building up a robot which contains lot of motors, etc. So, the electrical and magnetic property becomes important. Okay? So, there you have to talk about things like resistivity, dielectric constant, magnetic permeability, etc. Then we have to also think of the wear, tear, corrosion. So, that is the environmental interaction, that is oxidation, corrosion, wear, etc. Then other group are the production group, that is ease of manufacturing, joining, finishing. So, that is the production group. And last but not the least, the aesthetic is important. Okay. So, when we select a material, its look, its luster, its color, its texture, all these things are important. Okay. So, that comes in the aesthetic groups. So, these are the broadly, if we will be discussing in the course, and however in this week our focus will be the mechanical domain part of it, okay, where we are not only going to confine us with these properties, but many other properties we are going to look into the detail. Okay. So, now let us look into the mechanical properties and at least first look into it, that which mechanical properties, if I have to design a product, are primarily important, that you have to have a look on it. Okay. So, the very first group are something that deals with the elastic properties. Okay. Why? Because you know already that for stiffness dominated design, the elastic properties play a very important role. So, elastic property when we look into, then of course, there are different elastic properties. Okay. One of them is the Young's modulus, which deals with the linear deformation. So, that is the Young's modulus part of it, and then that is important for axial stiffness as well as for the bending stiffness. So, for design of things like a beam, like a frame, like a machine tools, okay, wherever the sort of axial deformation is predominantly axial in nature, there the Young's modulus play a very important role. For example, we are talking about a truss. Okay. So, your deformations you are expecting always in the axial direction. So, for all such elements, it is important that we actually consider the modulus of elasticity. And a similar thing is also true when an element is subjected to bending, because there also it is essentially the axial tension in one part and axial compression in other part. So, there also modulus of elasticity plays a very important role, the Young's modulus of elasticity. Now, I also said that there are other applications, for example, shafts, couplings we just discussed, or gears, in which case the loading is predominantly torsional in nature. So, for such a case the torsional stiffness becomes important, and for that the shear modulus plays the more important role than the Young's modulus. Some cases are there, cases like pressure vessels or seals, okay, or like another interesting case I did not mention here, that is when you are sending something in the under ocean. Okay. So, such application, like say for example, one good application can be this ocean bottom seismometers, we call it ABS. Okay. Okay, or you are sending some underwater vehicles. Okay. So, or say underwater vehicles. Okay. So, all these cases there will be actually a large hydrostatic pressure on the system. Okay. So, here we are not dealing with how something is actually getting expanding or contracting, but how the entire volume gets squeezed because of the huge pressure. Okay. You know that one of the starking failure was one submarine system, okay, which failed when it was under the closer to the ocean bottom, just observing the Titanic. Okay. And this type of failure is called implosion failure. It is not explosion, but implosion means the tremendous pressure, hydrostatic pressure of kilometers of these ocean water that is above you, actually collapses the system. So, for such a case the bulk modulus plays a very important role, which is a volumetric compression. Now, of course, other than this, whenever something happens in one direction, we know that because of this Poisson's effect, it is going to affect the other direction also. So, for example, I am trying to expand a beam, okay. So, using a force, and definitely if you look at it, that it is going to expand, but it is going to be narrower in the other direction, right. So, and that change here, okay, to a narrower one is actually the Poisson's effect, right. So, now some materials, most of the natural materials have a positive Poisson's ratio, okay, whereas some materials that we are able to synthetically develop today are having a negative Poisson's ratio. So, essentially Poisson's ratio tells us that what will be the effect of a particular load on the direction which is perpendicular to the force that you are applying for. So, this Poisson's ratio becomes an important factor, and all these things together comes into your group of elastic properties for stiffness control design. Now, if you say, well, it is the strength which is more important for me, not the deformation, but actually how much force or load it is going to sustain, then we will look into properties like the yield strength. Okay. Soon from the stress strain diagram we will see what it is, but its significance is there in terms of the plastic deformation. If we have to avoid the plastic deformation, that means any deformation which cannot be recovered once the load is withdrawn. So, that kind of a situation if you want to avoid, then you have to see that the applied load is not exceeding the yield strength. Okay. In fact, we apply a factor of safety and keep us well below the yield strength. So, that is one important property, and then similarly for the shear case, we keep a shear yield strength. If the sigma y's are related to the axial yield strength, it can be sigma y in tension and sigma y in compression. Then the other case tau y is for the shear yield strength, and that is important for shaft and torsion applications where you do not want it to fail in shear. Then of course, there is this ultimate tensile strength. Ultimate strength actually, as I told you, that beyond plastic deformation finally the failure happens. So, it is not just that the failure happens exactly when you cross the yield strength, but a little more than that in the plastic deformation domain the failure happens. So, there the ultimate tensile strength is important for us, that how much maximum it can tolerate. And then of course, the compressive strength for columns and concrete, that is important, and bearing strength, which is generally referred as sigma b. So, that is important for the bolted joints, for riveted systems, etc. So, this group is the strength related group, and that is mostly to sort of keep us safer, so that the onset of plastic deformation does not happen in the mechanical system. Now, we will have the third group. So, after deformation and after strength, the third important group is the fracture. Okay. So, fracture actually talks about the crack initiation and crack propagation. Okay. One important thing that is there is that every material, or let us say most of the materials that we use for mechanical applications are having cracks in it. Okay. It is only the size of the crack and the density of the crack that changes, but every material has some density of crack and some sizes of cracks in it. Okay. So, what is important for such situation is to know that, okay, fine, I know there is a crack there, but is it going to create a collapse? For example, I am thinking of a beam now, and I know that there is a crack here. So, as long as when I am applying the force, this crack is not growing further and sort of finally break the beam, I am safe. Okay. So, in order to know that, some properties becomes important for us, mechanical properties like the fracture toughness KIC, okay, which essentially talks about the resistance to the crack, and then the critical energy release rate or GIC, okay, particularly for a composite fracture, because the fracture can happen in many ways. There are fracture in a first mode, second mode and third modes, etc., which we will later on discuss, and in all such cases the corresponding propagation is actually predicted from the critical energy release rate. And then another very useful criteria towards this direction is the impact toughness. That means, if you really hit something with an impact load like Charpy test, then you know how much of the sudden loading it can take. So, that is the fracture related properties, that is the set C we have to keep in our mind. And the next one is for cyclic loading, okay, because there are many mechanical systems which are subjected to cyclic loading. Okay. For example, okay, the aircraft, as you every time you fly up, you are going to get a high pressurization, so that in in a very rarefied atmosphere people can survive. So, then you have a high pressure, and then when you are touching down, you have to again open up the door and the pressure has to become same as the pressure at the ground. So, what happens is that every time a aircraft flies in the sky and come back, there is a high pressure to low pressure cycle that operates. Now, this pressure cycle can create a fatigue, and we will call it as a low cycle fatigue. Okay. When we will discuss about fatigue, I will talk more about these things. This is a low cycle fatigue. Another possibility is there. Let us say a shaft which is rotating at a very high RPM, okay, or let us say a blade rotating at a very high RPM. Now, for such a case, what happens is that if there is any asymmetry in the system, so there will be a stress that will be generated in it, and that stress will be repetitive in nature. So, if that happens, because this whole thing is rotating at a very high speed, so this also the cycle of high stress to low stress, the cycle of high stress to low stress, for example, if I plot sigma with respect to time, maybe with respect to a base value, there will be a continuous high to low stress. Okay. So, this in comparison to our that low cycle fatigue, that is this case, okay, where your cycle is of very longer time period, here this is a high cycle fatigue. Okay. So, this these are two important applications. Now, towards that direction, there are three important properties that you always sort of check. Okay. One is called what is the fatigue strength, okay, and that actually says that maximum cyclic stress for a specified number of cycles, okay, without failure, right. So, that means if an objective we predict, for example, in aircraft or marine applications, we say that the system should be such that it can take 10,000 cycles or 100,000 cycles. That means after 100,000 cycles you have to change it, but the question is within that whether it is going to fail or not. So, sigma f talks about that maximum cyclic stress for a specified number of cycles, okay, whatever it is, that is the fatigue strength for the system. Then there is another thing also, that is called endurance strength. Okay. This is different slightly from the fatigue strength, in the sense that in this case we know that for any material, if the stress it is subjected to is within a certain limit, then actually it can go theoretically up to infinite cycles, particularly for ferrous materials and ferrous alloys. So, there the endurance strength becomes important for us, that is stress amplitude uh, below which the material can theoretically endure an infinite number of cycles. And finally, of course, the number of cycles itself, NF, that is the total number of cycles to failure under a specified cyclic loading condition. So, all these three things becomes important for the fatigue related properties. So, we said deformation, we said strength, we said fracture, we said fatigue, and we always say that a material to be chosen for product design must first survive this 4-dimensional requirement. Once this 4D requirement is done, then there comes other important requirements. For example, creep. Creep is like when you are applying a load for a very long time, whether there is a change that is happening in the system. Hardness, okay, wherever there are relative contact between the two surfaces, the hardness is important. For example, for a railway line, the hardness is important for us. Wear, another thing, so that it does not lose the material. Other similar tribological properties due to contact. Resilience, so that how much of energy you can absorb in a system. Toughness, impact strength, damping capacity. So, all these things becomes important for the other mechanical property groups. Now, we always, how do we actually use these mechanical properties? Okay, why we use these things? So, the advantage of doing this is that you get always a deterministic analysis if you do first the statistical analysis of the material itself, because then you know from your test data that what are the different variations and what are the different ranges for each and every property. And once you know it, you can integrate it in your design guidelines, and then you can see that whether it will be profitable or not. Suppose a material tells you that you can use it for 5 years or 10 years, okay, then okay, I am investing this much of material for building up a system, and this is the cost I can sell. So, it is going to be a business case or not. So, always material properties, obtaining them directly experimentally helps us a lot towards that direction. Now, I told you that the first group of properties, that is A and B, that is the elastic deformation and the strength, both of them needs some basic concept of stress and strain. Okay. So, in the case of stress, that is the internal resistance force, resistive force per unit area acting on a material. Okay. And we have to keep in mind that it is not really an average force that is applied over an area. Okay. Rather, we should define it in terms of a limit, that limit of this ratio as A tends to 0 is actually the stress. Okay. So, even though you can simplistically write it as F over A 0, but a stress is more rigorously defined as a limit A tends to 0, what happens to this F by A ratio. Okay. So, that then becomes the stress, and usually we represent it in terms of Newton per meter square, but you will see that during our talk we will go to kilopascal, megapascal and gigapascal pretty often. Okay. So, I do not define it at each and every time, but you can see it now that what does that mean, like 10 cube Pascal for kilopascal, 10 to the power 6 for mega and 10 to the power 9 for giga. Now, when I am talking about the strain, it also is implicitly understood that the force, corresponding force to generate a stress, can be either towards tension or towards compression. So, you can have a tensile stress as well as a compressive stress. And what is the strain then? Strain is simply what is going to happen in terms of deformation, and we are going to always measure it as change in length over the original length. So, that is the delta L over L, okay, and this is also known as a engineering strain or conventional strain or normal strain, and strain is going to be dimensionless, and we generally refer it as in terms of a micron strain, which means something of the value of 10 to the power minus 6. So, that is the stress and the strain concept. Now, there can be another type of stress, that is the shear stress. Okay. In this case, you are applying the force on the surface, not perpendicular to the surface. So, that is like we have seen it in the last class for torsional design, how the shear comes. So, that is the, with respect to these surface, the top surface has moved by an amount delta, and hence for such a case the strain, the shear strain, which is known as gamma, is delta over L, and essentially if you look at it geometrically, this is nothing but the tan theta, and for small strain you know that the tan theta becomes equal to theta. So, that is what is the shear strain, and the shear stress is force over this area, which will be something like, you can see a single shear, a double shear. So, force, whatever force it is coming, like F by 2 in this case, and whatever area over which it is going to work on. So, that is the shear stress. So, shear stress to shear strain relationship and axial stress to axial strain relationship, both of them are important for us. The other important thing is something that generates the shear, that is the torsion. Okay. So, in the case of a shaft like this, you can see that the torsional equation defines that what will be the relationship between the torsion that you are applying and the shear stress that it is going to get generated. They are implicitly related to each other. So, these are the things, and the common states of stress, as I told you, very common states of stress are simple tension like this case, simple compression like a column, or a hydrostatic pressure on anything that is submerged or balloon, and then the pure shear for bolts, etc. So, these are the different common states of stress that we generally any product will come across. So, I will close the first part here. Thank you.